We already know what happens if you put a portal's exit into its entrance. It comes out of itself and hits the edge. But what if you make it small enough so it fits? You've asked me this countless times and I was curious myself, but it broke in my program and I had no idea how to solve it. Until now. I finally have the solution, let's check it out. Look at this tiny portal. It's moving forward, and it emerges somewhere. Let's revolve around. Wait, where did it go? The portal created a pocket dimension? Yes, and this is the correct answer, which we'll explore in detail in this video. The key to all of this is one overlooked portal axiom that not only explains this result, but also unlocks amazing new possibilities for other portals, and completely flips our understanding of portal physics. You are on the Optozorks channel, my name is Ilya, let's get started. Let's take two portals. They can teleport an object. If we turn off light teleportation, then we can see the teleporting surface. When crossing this surface, an object or light teleports to the other portal. That's exactly how it works in my program. When a light ray hits this surface, it jumps to another location and keeps going. In one of my previous videos, I showed an axiom that says a portal's behavior doesn't depend on the shape of its surface. So we can make it hemispherical and nothing really changes. Let's dive into how this works. First, let's look at how a light ray behaves with different surfaces. A light ray that starts here and going in this direction doesn't change at all. But if we make the shape hemispherical, the light ray first teleports to the orange portal, then back to the blue one, and ends up in exactly the same spot as with the flat surface. This explains why changing its shape doesn't affect how portal looks. Object teleportation works the same way. But look, with a flat surface, the back part is flat, but with the other surface it looks completely different. That doesn't really match our axiom. To solve this problem, we can turn the back surface into a portal too. It turns out this axiom only works for two-sided portals, which we haven't explored before. By the way, notice that at some point the object doesn't actually teleport, but it looks like it did, as if the teleporting surface is drawn around it. What if we do the same with the portal? Let's take an ellipsoidal portal with a similar surface and place it inside itself as far as it can go. And here's how it looks with light teleportation. Now it looks like the orange part teleports the blue part, although this doesn't actually happen. Remember how I used to do this before? I created multiple degrees of teleportation and filtered them in a special way. So I could have skipped all that work and just made such teleporting surface to get the same result? Well, it turns out these approaches are equivalent. So the next logical step is to take a small portal with a hemispherical surface and simply place it in the orange part. And that's the entire solution. Inside we get a pocket dimension. Later in the video we'll discover if it can be moved indefinitely, figure out how infinite space emerges, and conduct many experiments. But first I want to tell you how I came to this discovery. After publishing my previous videos, I thought I'd shown absolutely everything possible and there was nothing left to discover about portals. Scrolling through Twitter, I found this message. You can actually put a portal inside itself fully by using the half-sphere portals. I thought, nothing interesting. The guy just moved a portal. Of course, a small hemisphere will fit in a large one. But hemispherical portals work exactly the same as flat ones? So he placed a flat portal inside itself? I was flabbergasted. This discovery is what led me to quit my job and focus on YouTube to make this video. And this guy deserves credit. He did this using a scene editor to get this result. Before that, I had tried to solve the small portal problem in a million ways, analyzed all possible matrices, tried different calculation methods, but nothing worked and I eventually gave up. But let's figure out why exactly this axiom is true beyond the fact that it just looks right. There are two types of portals, scanner-printer and spatial. A scanner-printer portal scans and destroys an object on one side and recreates it on the other. This would need tons of energy, and this kind of portal could theoretically exist in our world. But it disobeys our axiom, because it has only one active surface and its shape affects its behavior. Later in the video, I'll propose an experiment to measure this surface. Now about the spatial portal. I borrowed this clip from the video The Shape of Space, which I highly recommend. It shows how a torus unfolds into a flat sheet of space. A torus has such a structure that in the flat version, the right side leads to the left and the top leads to bottom. You could say this works just like portals. And these portals create this shape in the form of a torus. So, what would the shape of a space look like for our portals? To show this, I wrote an entirely new program capable of simulating this curvature of space. For example, this is how a flat torus looks in it. We see that the blue square teleports between top and bottom, while the green square teleports between the right and left edges. My program glues left to right and top to bottom. Then it runs a simulation to which shape this will lead to. It moves in a funny way and converges to a torus. With this torus, both squares end up continuous. Next, let's take this scene on a plane. Here we have a two-sided portal. The blue square teleports and moves in a circle, while the green one simply teleports. In the simulation, this part of the portal is glued to another part. I start the simulation and it converges to this shape. As we can see, the green square doesn't appear to teleport at all. And if we rotate the view, we can see a cylindrical surface in the back, and the blue square moves in a circle within it. And when viewed from this angle, it resembles a visual representation of a wormhole. Now let's examine a portal with a different teleporting surface. Similarly, this surface in one place is glued to this surface in another place. We start the simulation and it converges to exactly the same shape. You could say that portals in this configuration inherently define this shape, and the teleporting surface is simply our choice of how we cut through that shape to represent space in a flat way. This means the teleporting surface is a virtual entity, something we use for our convenience. And that's exactly what justifies the axiom introduced in this video. From here, we can derive many interesting things. For example, a doorway and a portal represent the same local space. Furthermore, we could say that a portal doesn't just have one teleporting surface, but that all possible surfaces exist simultaneously, and at the same time, none of them truly exist. Also, for a spatial portal, there is no such thing as before teleportation and after teleportation. Now let me clarify that I am using hemispherical portals only because they are easier to program. In reality, the surface can be anything: flat, hemispherical, zigzagging. It can even intersect itself. The only constraint is that the one part must not intersect the other, as shown here. But actually, even a broken surface like this can be fixed. We just need to teleport this piece to the orange portal. However, I avoid doing that, because those are the same calculations as degrees of teleportation, and they are not easy to implement. This is just a quick tour of my new space curvature simulation program. I haven't explained how it works, why there are holes here, what the Nash embedding theorem has to do with this, and much more. In the future, I'd also like to simulate the curvature of space for a portal inside another portal or for a moving portal. But all of this will take a lot of time and effort. Let me know if you want a dedicated video about that. Now for the experiments. Let's see how an object passes through such a portal. Without light teleportation enabled, nothing unusual happens. The object simply gets bigger. But when light teleportation is on, we see multiple copies of the object. It's important to understand that these are only reflections. There is always just one object. You can't physically duplicate it. You can even rotate the view inside the portal and look at all these reflected copies. This leads us to the next question. How does infinite space appear inside the portal? And why it is so dark in there? I created a new feature for the camera. Now it can teleport through portal. To demonstrate this, we rotate inside a portal within a portal scene. Here's how it looks with light teleportation. And here it is with both modes enabled. Each time we teleport, we see only two hemispheres. But because the portals work so seamlessly, we don't notice the transition. This is how infinite space is formed. With each teleportation, you become smaller and smaller, which means you can fit infinite space inside a finite volume. By the way, I want to emphasize that pocket dimension technically exists right here, between the two portals. Nothing actually separate from the universe is created, it just appears that way. So, why is it so dark in there? Because many light rays get stuck in teleportation loops. We can demonstrate this by flying in this direction. Let's turn on the dual mode display. As we fly, we see constant teleportation, but no visible exit. In my program, when a light ray gets trapped and teleports endlessly, it's rendered as black. Now let's take a look at another scene. Here, the two portals are facing each other, and the small one enters the larger one head-on. This resembles that GIF where two portals move toward each other. Or that video you've probably seen. With flat portals, this would be an unsolvable situation. But now we can place the small portal inside. We fly through it and turn around. And we see a pyramid of all degrees of teleportation, stretching in both directions infinitely. It's still just one portal, but the space is folded in such a way that we perceive multiple copies. Just like with the object, there is only one instance. And can we move this portal forward infinitely? Let's take this shape and move it. As soon as it touches its own surface, everything breaks. One part of the surface begins to intersect the other. But since the portal is smaller, we can keep increasing the length of its surface indefinitely, allowing it to move farther and farther without intersecting anything. So yes, the portal can move forward forever. And this is what it would look like. Just make sure not to drop anything in such a portal, or it will be lost forever. For instant movement in other scenes like this one, we need to change the shape of the surface in a smarter way. But it's generally possible. This is the main limitation of this surface shape approach. The surfaces must not intersect, otherwise the image breaks and becomes nonsensical. It turns out we can't come up with a single portal surface that will work in all cases. For each individual case, we need a new surface shape. For example, let's recall these ellipsoidal portals. Here the hemispherical surface has reached its limit. It touches the boundary, we can't enlarge it anymore. But with light teleportation, we see that the portal hasn't fully entered the other portal. My flat portals with degrees of teleportation worked perfectly in such situation. So we need to devise a new, more complex surface shape for the portal to fully enter here. Or we need to somehow combine these two approaches into one, so that it can solve all possible problems. I've already found a solution and it's very unusual. But more on that in the next video. Also in the next video I'll show whether it's possible to put a normal sized portal inside itself. So be sure to subscribe so you don't miss it. Another reason why this is an incredible discovery is that this idea can even be generalized to the triple portal, which I showed in this video. The regular triple portal is one-sided, because it has this closed back surface. And to make it two-sided, you need to add another portal to each part, so that each part looks like the letter Y. Now our axiom works for this portal. This means we can create a non-flat teleportation shape like this, using a third of a sphere. It's quite non-trivial shape, but it works exactly the same as ordinary triple portals. And since we have such a shape, now we can place two portals into another one. Let's say like this. Let's get closer, turn on light teleportation, and we can revolve inside just like we did for other portals. Here we get such a beautiful and complex fractal because the triple portal connects space in a more complex way. And the same can be done with a cylindrical portal. Here you can inflate the surface like this, and the portal will work exactly the same way. Now let's shrink one part and place it in the center. Next, let's fly in. We see that there is an infinite black space again, and the portals are arranged in the shape of an hourglass. Let's turn off light teleportation and inflate the surface again, so that the portal can move beyond the flat boundaries. And now the same movement but with light teleportation turned on. And from this position you can rotate this portal. This new approach is perfect for creating mesmerizing animations. Or you can rotate it another way. It's interesting how the angular velocity of rotation increases to infinity as the size decreases. Now about the physics. Let me clarify that I'll be using the terms before teleportation and after teleportation because it's easier to program and reason about different surfaces. And it's easier to understand what leads to contradictions and what doesn't. We need to remember that no place before or after teleportation exists anymore. Let's take this scene, which we've already discussed in one of my previous videos. There is no gravity or air resistance here. The portal moves uniformly and in a straight line, by inertia. It has no acceleration and it doesn't stop anywhere. Before teleportation, the object is stationary and it moves after teleportation. People don't like that the object somehow gains momentum in this scene. After all, portals work like doorways, and when a doorway runs into you, nothing happens. Yes, because in a doorway, the entrance and exit move at the same speed relative to each other. But in this case, they move at different speeds. People probably assume that the portal should behave something like this, when the object stops immediately after teleportation, to avoid gaining any momentum. We remember that this can be the case, because there is no moment after teleportation. But let's try to follow this logic. I think everyone agrees that the object should be stationary before teleportation, right here. So here's the big brain move. What if I make a teleporting surface like this? Here the object never teleports, and it's always stationary. But it looks as if it teleported and gained momentum. As we remember, any law of portals must work the same for all surfaces. So for this scene, the only working option is the movement after teleportation. This kind of stopping can only work for one, flat surface. But movement after the teleportation works for any surface. But this is only if we accept this axiom, which gives such incredible results as pocket dimension. Let's continue. In this scene, the portal moves in a circle instead of a straight line, which means it's constantly accelerating and changing direction of its speed. Let's add an object here, and now the question is, how will the object move after teleportation? The first option, it will move in a straight line. Look, before teleportation, it moved in a circle. This is the gray trajectory. And after teleportation, it started moving in a straight line by inertia and acquired rotation. This fits a scanner printer portal, which have a specific surface that exerted force on the exiting object. So now it moves according to the normal laws of physics. And this is a way to measure the surface of a scanner printer portal when we can't see it. In the same situation, we launch multiple objects before teleportation. They move in a circle and then they start moving in a straight line. If the surface were different, for example hemispherical, the objects would start moving in a straight line at a different moment in time. And by using this, we could calculate this surface. The second solution to this problem, the object continues to move in a circle. This fits perfectly for spatial portals. And that's because we can design such a surface where the object never teleported, but it looks like it's moving in a circle. This is even better seen if you stand in the object's position. So what does this mean? It looks like action at a distance that applies to everything that passes through portals. If you entered a portal and it started moving differently, then this will affect you from any distance. This is absurd. This is a very bad result and a real reason to doubt our axiom. Or something else need to be rethought. And now my favorite picture. If you don't know it, pause and decide what you choose. I've always been for option B, where the object flies out of the portal with some speed. And I never understood supporters of option A, where the object stops immediately after teleportation and slides down. But now I understand that there is more than meets the eye. This picture is essentially a combination of the two previous scenes. First, the portal moves without any acceleration at a constant speed, and then it stops. And this stopping moment is what I've been ignoring all this time. After all, this is accelerated movement which gave us an absurd in the previous scene. Now what if we make a hemispherical teleporting surface for the portal? When the portal stops, it never teleported anything, and the object was always in its original place. So then option B is correct for a flat surface, and the option A is correct for hemispherical surface. And which one to choose? I don't have an answer, but I have something better. Direction to an answer. Portal gravitational waves. I think that an accelerating portal should emit something like gravitational waves that propagate at the speed of light and affect objects. Thus, we can avoid action at a distance. It seems that when stopping, the gravitational wave should somehow slow down the object, and the final answer should be something in between A and B. But to research this, one needs to know the theory of relativity and its math. But I am not familiar with this. So, my friends, I will leave the physics to you, while I responsible for the geometry. But again, this is just an idea. Maybe I'm wrong and everything should work differently. As always, you can try out everything that I showed here in my web demo. And now there is another one too. For the next video, most of the work is already done. It will be coming soon. By the way, now I have a Discord server where you can chat about portals. And thanks for watching.